All right, so moving on to the idea of vapor pressure and dynamic equilibrium. This is related to what I was saying before about if you have, say, a liquid like water in a closed container, then there will eventually be an equilibrium between evaporation and condensation. This is known as a dynamic equilibrium because it's an equilibrium because the rate of evaporation will be the same as the rate of condensation. And it's dynamic in the sense that things are actually changing at the molecular level, even though they don't appear to be changing. There's no overall change in the concentration of the liquid water or the concentration of the water vapor, but there will be a change in which individual molecules are in the liquid phase or the vapor phase at any given moment. So you've got molecules that are sort of going back and forth between the vapor and the liquid, but they're going in both directions at equal rates. Okay, so it looks like nothing is changing, but you've really got individual molecules that are evaporating and condensing at equal rates. Okay. The vapor pressure is basically the pressure of a gas that's in equilibrium with the liquid version of the same substance. So the vapor pressure of water is basically the pressure of water vapor above liquid water when the two are in equilibrium with each other. And when they're in equilibrium with each other, that's basically in a closed container. And actually, every liquid will have a vapor pressure. And in fact, some solids have a measurable vapor pressure too, because of sublimation, where you can go directly from the solid into the gas phase. But definitely every liquid will have a vapor pressure. And the vapor pressure can change with things like temperature. And of course, the identity of the liquid. It depends on the identity of the liquid because that has to do with what types of intermolecular forces are present. And it also depends on temperature. So say if it's water, the vapor pressure of water will actually change as the temperature changes. If you're comparing, say, two substances at the same temperature, say water versus alcohol, then you'll have two different values for the two substances, even though they're at the same temperature. Volatile liquids. Meaning liquids that evaporate easily. or liquids with low boiling points tend to have high vapor pressures. And those would be things like alcohols, gasoline, and so on. They basically, high vapor pressure is just another way of saying that these are substances that evaporate quickly. If you bring a can of gasoline into the house and open it, you'll be smelling that gasoline all over the house in no time because it's evaporating so fast. And once those molecules are in the gas phase, they can move around at a high rate of speed and they really spread fast, and you'll be able to smell them all over the place. Alcohols are usually used as the basis for perfumes because the alcohols themselves evaporate very quickly, especially when you put them on your warm skin, and they help, that evaporation helps carry the scent of the perfume all over the place. And that's generally considered desirable, I guess. Non-volatile liquids. Those with high boiling points, they have low vapor pressures. And these would be things like oils, motor oil, as well as things like olive oil and that sort of thing. And water would be somewhere in between. Moderate vapor pressure, because it is somewhere between volatile and non-volatile. Okay, so you can sort of think of vapor pressure as being like the pressure of the liquid pushing out against the atmosphere. And then you've got the atmospheric pressure pushing back on the liquid, saying, oh no, you're not going to become a gas. There's already too much of us out here. You're going to stay a liquid. So you got the vapor pressure of the liquid pushing out against the atmosphere, trying to become a gas. And you've got the atmospheric pressure pushing back on it, trying to keep it to be a liquid. And it's that balance of forces that kind of determines whether evaporation or condensation will win the day. Systems that are at equilibrium, so it's like a liquid in a closed container, will eventually reach an equilibrium between evaporation and condensation. Tend to try to maintain that equilibrium. To the extent that if something happens that disturbs that equilibrium, the system will react generally in a way that will tend to restore that equilibrium. So an example of that might be if the volume of a container is changed without opening it up, because if you open it up, you lose the equilibrium. But so if the volume of the closed container with liquid and vapor in equilibrium is increased without opening it up, then what will happen is the pressure of the vapor above the liquid will drop. Okay, the result is more liquid evaporates. And the pressure ends up right back where it was. And that process basically continues every time the volume increases until all of the liquid is gone. The opposite will occur if the volume decreases. So if the volume decreases, the pressure of the vapor above the liquid will increase, and more molecules in the vapor will condense to the liquid. And the pressure ends up back down where it was originally. And that's because you'll end up with fewer gas particles in a smaller area, and that will make for the same pressure overall as you had before. So when a system that's at dynamic equilibrium is disturbed, it responds in a way that minimizes the disturbance and restores equilibrium. And this is known as Le Chatelier's principle. This is something that you're going to hear a lot about if you take Chem 121, because there's an entire chapter on equilibrium situations, and this will come up quite often in that context. And so this is a good introduction to that idea. And we've already explained basically one way, or two ways actually, that a system can respond to disturbance in order to restore equilibrium. Okay, as we've mentioned, vapor pressure can depend on temperature. And boiling point as well. And so we know that if the temperature of a liquid increases, the vapor pressure increases. And that's because more molecules will have enough kinetic energy to escape and evaporate into the gas phase. And that's essentially what the vapor pressure is. It's the molecules that have enough energy to leave the liquid and go into the gas phase, pressing out against the air above the liquid, trying to do just that, become a gas. So if you increase the temperature, you increase the number of molecules that have enough energy to do that, and that has the result of increasing the vapor pressure. So if the pressure goes up, the vapor pressure goes up. If you add enough heat that you can get to the point where the vapor pressure is equal to the atmospheric pressure, then basically all of the molecules in the entire sample of liquid will have enough energy to escape into the gas phase. And that is the boiling point. So when enough heat is added that the vapor pressure of the liquid is the same as the atmospheric pressure, the liquid begins to boil. So if you recall that the vapor pressure is created by molecules of the liquid that have enough energy to escape into the gas phase, and they're kind of pressing out against the atmosphere, trying to become liquids. And you have the atmospheric pressure, which is air or whatever the atmosphere is made up of, pressing back on those liquid molecules saying, oh no, you don't, you're going to stay a liquid. And if you get to the point where those two pressures are equal to each other, then both processes can occur. You've got vaporization occurring, where these particles can come out of the liquid into the atmosphere, and at the same time, some of them will be returning to the liquid. But usually the rate of the vaporization will be faster because this is normally happening in an open container. And once the liquid particles vaporize, there are gases and they tend to move away from the container fairly quickly, and they're lost. They can't recondense into the liquid if they're not there. And so the vaporization tends to occur more quickly once this point is reached. So what this means is that essentially all molecules in the liquid including those in the interior, have enough kinetic energy to become a gas. So the boiling point is actually defined as the temperature at which the vapor pressure of a liquid is the same as the atmospheric pressure. There's also the concept known as the normal boiling point. And the normal boiling point just refers to the boiling point at 1 atmosphere. So in other words, the normal boiling point is the temperature at which the vapor pressure of the liquid is equal to 1 atmosphere, because that would be your normal atmospheric pressure. The general definition of boiling point up above can be applied to any atmospheric pressure. So whenever the vapor pressure of the liquid is equal to the atmospheric pressure, whatever that might be, that's your boiling point under the given conditions. The normal boiling point would be when the vapor pressure is equal to 1 atmosphere, because that's considered normal pressure. And so the boiling point depends on several things. Well, first of all, the identity of the substance. Because, of course, the identity of the substance has to do with what kinds of intermolecular attractions are present. And that has a lot to do with how much energy it takes to tear these molecules apart from each other and put them into the gas phase. It also depends on atmospheric pressure. I think I mentioned before about how places like Denver, Colorado, that are far above sea level have to have special cooking instructions for anything that involves boiling water, because their atmospheric pressure that far above sea level is significantly less than it is at sea level. And so you need less heat to boil water in Denver than you do here in Buffalo. And so the boiling point of water in Denver is actually significantly less than it is here in Buffalo. I think it's around 90 degrees Celsius or something like that in Denver. So you basically anything that involves cooking something in boiling water, it takes longer because the boiling water is not as hot there as it is here. So it depends on atmospheric pressure. Also, pressure cookers are used because essentially pressure cookers are pressure vessels that can withstand pressures above normal atmospheric pressure. And so in a pressure cooker, you can heat something up in water, and at 100 degrees Celsius, where the water would normally boil off and go off into the air as steam and be lost, the pressure cooker actually keeps that steam in and allows the pressure to build up. And that extra pressure within the pressure cooker keeps the water in the liquid state to temperatures that are higher than 100 degrees Celsius. And that allows things to cook faster because you can get the water up to a higher temperature before it boils off. Also, I think I've mentioned before that you can actually boil temperature, or you can actually boil water at room temperature just by lowering the pressure on the water. So if you take a little beaker of water and put it into a vacuum chamber, and if there's a viewing port on the vacuum chamber, you can actually watch the water boil as the pressure goes down, even though the pressure chamber is cold to the touch. So the water is actually boiling at room temperature because you've lowered the atmospheric pressure around the water enough that the vapor pressure is equal to the atmospheric pressure at room temperature. The temperature will remain at the boiling point throughout the vaporization and will not go higher until all of the liquid is vaporized. That's assuming that you're able to capture the vapor and continue heating it, which is basically what a pressure cooker does. But like I said, normally if it's an open container, then the vapor will go off into the air and will be lost and you won't be able to heat it anymore. Okay, so let's look at vapor pressure. There is an equation that allows you to predict the vapor pressure of a liquid at various temperatures. But it is possible to predict vapor pressures of liquids at various temperatures, but it's not always easy because the vapor pressure does increase with temperature, but the relationship is not linear. And with various really common substances like water, you can actually just go to tables that are readily available and look up the vapor pressure of water at a given temperature. And then you got it, and that's all. That's all you have to do. But for other substances, tables of vapor pressures versus temperatures are not always that easy to come by. In the internet age, I guess that's beginning to change. But in the old hard copy paper and book days, basically we needed to use an equation to figure these things out. And so vapor pressure, or P-vape as I'm going to call it for the next little while here, increases as temperature increases, but the relationship is not linear. So it doesn't increase linearly with temperature, and the relationship is different for different substances. And so we have this equation that's known as the Clausius-Clapeyron equation. And that allows us to calculate the vapor pressure of a liquid at various temperatures. And all we have to know is what the temperature is and the heat of vaporization. So you can calculate the vapor pressure of a liquid at a given temperature, and all you have to know is the heat of vaporization. The equation takes the form of let me see. The natural log of the vapor pressure is equal to the natural log of the exponent of negative delta H vape over RT. And that looks kind of nasty. And so you can actually rearrange that and come up with a different arrangement. And what we end up with is the natural log of the vapor pressure is equal to negative delta H vaporization over R times 1 over T plus natural log of beta. And to explain what some of these things are, beta is a constant that depends on the gas. And you can look those up. There are tables of the beta constant for the Clausius-Clapeyron equation. Ln is a natural log. That is a log to the base E. And all you really need to know about that for our purposes is that when you're using natural logs, you hit the Ln key on your calculator instead of the LOG key. You hit this one instead of this one. R is the gas constant, but it's the energy version of the gas constant. So it's 8.314 joules per mole Kelvin. And T is the temperature in kelvins. And the reason actually that we tend to use the Clausius-Clapeyron equation in this form is that if you're familiar with the equation for a straight line, it's usually rendered as y equals mx plus b, where x and y are the two axes, and m would be the slope of the line, and b would be the y-intercept. Well, look what we've got here. Y equals mx plus b. I mean, it's even beta, which is the Greek version of b. So what we have here is an equation that will give us a straight line if we plot it out. So a plot of 1 over temperature in kelvins on the x-axis versus natural log of the vapor pressure as the y-axis will give you a straight line. And the slope of that straight line will be the heat of vaporization over R. And the point where it crosses the y-axis will be the natural log of beta. As I said, beta is readily available. You can look it up in tables for all kinds of different substances. As it turns out, vapor pressure is relatively easy to measure in the laboratory. And so most often, this equation is used to calculate the heat of vaporization for various substances, because that is a little more difficult to measure in the laboratory than vapor pressure is. So what you'll usually do if you want to use this equation is you'll do an experiment under several different temperatures, and you'll measure the vapor pressure of the liquid under those different temperatures. And then basically you'll plot the results of natural log of the vapor pressure versus 1 over the temperature. And you'll find the slope of the straight line that results. And you'll take that slope times R, and that will be, then you'll change the sign, and you'll have the heat of vaporization. And so that's what it's actually used for most often, is the heat of vaporization. Okay. You can actually also use any 2 points on a Clausius-Clapeyron plot and you can use what's known as the 2-point version of the Clausius-Clapeyron equation. And that is natural log of P2 over P1 is equal to negative heat of vaporization over R times 1 over T2 minus 1 over T1. So this is another way that you can find the heat of vaporization, or you can find the vapor pressure. So this is known as the 2-point version of the Clausius-Clapeyron equation. To basically find the vapor pressure of a liquid at any temperature if you know its heat of vaporization. So you're going to find the vapor pressure of a liquid. And all we need to know is the vapor pressure at another temperature, or the substance's normal boiling point. And its heat of vaporization. Because if you know its normal boiling point, you know that the temperature is, whatever the normal boiling point is, and the fact that it's the normal boiling point means that the vapor pressure at that temperature is 1 atmosphere. Okay, so that's helpful. So an example of that might be, say, propane. Has a normal boiling point of negative 42.0 degrees Celsius. And what that means is the vapor pressure of propane at negative 42.0 degrees Celsius is 1 atmosphere. That's what normal boiling point means. At that temperature, the vapor pressure is 1 atmosphere. And the heat of vaporization is 19.04 kilojoules per mole. What is the vapor pressure of propane at 25 degrees Celsius? Okay, so what we're going to need is our 2-point version of the Clausius-Clapeyron equation. So natural log of P2 over P1 equals negative H vape, heat of vaporization, over R, times 1 over T2 minus 1 over T1. And let's see, T1 is minus 42.0 degrees Celsius. And in kelvins, that's 231. Temperature 2 would be the temperature that's cited in the question. That's 25 degrees Celsius, or 298 Kelvin. Pressure 1, that is the pressure that goes with temperature 1, is 1 atmosphere. P2 is the pressure that goes with temperature 2, and that's the unknown. And the heat of vaporization is 19.04 kilojoules per mole, but watch out, it's got to be in joules because of the units for R. That's 8.314 joules per mole degree Kelvin. And so this is actually 19,040 joules per mole, because each kilojoule is 1,000 joules. So if we take natural log of P2 over 1 atmosphere, that's going to be the negative of the heat of vaporization, which is negative 19,040 joules per mole. And that's over R, that's 8.314 joules per K mole. And 1 over T2 is 1 over 298 minus 1 over 231. Let's see, we can work this out. Delta H of vaporization over R is negative 2290, and I believe that unit is K, because that's the only thing that doesn't cancel out here. And the we have here 0.003356 minus 0.004329. And the units here would be 1 over k, or k to the minus 1. And when you multiply this times this, you've got a negative times a negative. So it's plus 2.2282. And that will be, let's go to the next page here. ln, that is natural log of P2 over 1, which you can just ignore the 1 because that doesn't change anything, is equal to 2.2282. And so what we need here is going to be to find out what's inside the parentheses. P2 over 1, or just P2, is going to be the base of the natural log system, which is e to the 2.2282, or inverse natural log of 2.2282. Notice if you press second function and then, I don't know if you can see it on this one. Let's try the brighter colored one. I guess it's somewhat easier to see. You press second function and natural log. Notice what's written right above the key there, e to the x power. So pressing second function in natural log is the same as taking e, the base of the natural log system, and raising it to the power that you're entering. It's kind of the same idea as hitting second function and then log is the same as raising 10 to a given power. So if we do that, we get 9.28 atmospheres. And it makes sense that the vapor pressure of propane at 25 degrees Celsius would be way above atmospheric pressure, because propane at 25 Celsius is normally a gas. So, you know, obviously it's going, if it's a gas at that temperature, then normally it's got to have a vapor pressure that's greater than 1 atmosphere. And boy, that's greater than 1 atmosphere, all right. Okay, well, we're well past 30 minutes, so I'm going to call it time on this lecture, and we'll pick up here with the next one.